Welcome to the course Chemistry, Concept Development and Applications. My name is John Hutchinson, and I'm a professor of chemistry here at Rice University. If you're not familiar with Rice, we are a small, private, research-intensive university located right in the heart of Houston, Texas, and we just celebrated our 100th birthday back in October of this past year. I've been at Rice for 30 years now. I've been teaching general chemistry for about 25 of those years, and over that period of time I've developed a particular approach to introducing students to chemical concepts based upon the concept development approach. The purpose of this first lecture is to give you an exposure to what that concept development approach is so that you can have some understanding of where this course is going. To give you some context for this approach, what I'd like to do is describe what the sort of traditional approach to teaching general chemistry has been. The idea here is that fundamentally, of course, we would like our students to understand the most important chemical concepts that they need to take away from a class in chemistry. So our goal is, of course, these chemical concepts. The typical way in which this has been introduced is to simply describe those chemical concepts to students and then give them a variety of applications or really problems to solve based upon those chemical concepts. So in fact, the way in which we teach the chemistry is to teach how it is applied in context. This process is called deductive reasoning. Going from the general, the concepts, to the specific, the applications, is an example of deductive reasoning. And the fundamental assumption here is that if we can solve these chemical problems down here, that it must be the case that we understand the fundamental chemical concepts. But it turns out there's a lot of research over the past, say, 20 to 30 years in science education that clearly shows that this is not the case. That is, if I have a student who can work applications, and if I test their ability to understand chemical concepts based upon those applications, it turns out that's not true. In fact, it is entirely possible to solve problems in chemistry without understanding the chemical concepts at all. So what would be a better approach? A better approach is based upon this diagram here. This is the essence of the concept development approach. Notice here that we still have the fundamental chemical concepts as being sort of our highest goal. That's what we're really trying to get students to get to. And notice on the right side of the diagram back over here that in fact we still have these applications and we still have the deductive reasoning. But we've added a key additional part here, which is the idea that all of science is based upon experimental observation. We go to the laboratory, we collect measurements, we look at nature, we ask questions about nature, we analyze the answers to those questions about nature, and the process by which we go from those observations to the fundamental chemical concepts is a process referred to as inductive reasoning. If we look at the left side of this diagram over here, what we can see is that we are constructing our chemical concepts that we want to understand on the basis of experiments and observations. That is the essence of the concept development approach. How do we actually do this? Well, this diagram may help you understand that a bit, because this is the process by which we walk our way through the development of a fundamental chemical concept. It begins, in essence, in every case, with the development of a set of questions. What would we like to understand about the world around us that we maybe don't already understand on the basis of prior knowledge that we'll call foundations? The way that we answer those questions is not just to look at the textbook and see what the answers are, but rather to go to the laboratory and devise experiments which, in fact, will reveal to us something about the answers to our questions. And the first step in the process of analyzing those experiments is to try to develop some kind of a model that helps us understand the observations we've made and perhaps gives us some preliminary answers to the questions that we've developed. So we engage then in model building. A model is itself essentially a concept that helps us explain observations that we have made. Now, most chemical models, in fact most scientific models, will challenge us with more questions than the ones that we started off with. Therefore, we wind up developing a new set of questions here requiring new experimental observations. Those experimental observations will cause us to revise our model. And with that revised model, again, we should expect that there will be new questions which will be asked, requiring us to do additional experimental observations and further refinements of our models. Notice that we end this process sort of with the ... ellipsis there. The purpose of that is to demonstrate that in principle, in science, we keep doing this over and over again, and an iterative process by which we question, experiment, and define a model question, experiment, refine our model, until ultimately we've achieved answers to the questions that we originally set out to do. Why go through this whole process? Why, in fact, don't we just do what was on the previous slides and say, look, we're going to tell you everything you need to know? There are a variety of reasons why we would use this concept development approach, what my students commonly call the CDS. The first of these has to do with learning styles. Turns out most of us are, in fact, inductive learners. Most of us like to look at the world around us, look at specifics, and then build generalities out of those specifics. The generalities mean more to us when we have developed them out of observations which we have made. Maybe more importantly, science is inductive. In fact, the entire scientific method of setting out hypotheses, testing those hypotheses against experimental observations, and then the development of models or even theories, that is inherently an inductive process. So we should learn how to do scientific reasoning by, in fact, learning how to do inductive reasoning. In addition, it turns out there's a whole theory of learning called constructivism that says that we are far more likely to internalize, understand, and even retain our understanding of complicated material when we have constructed it ourselves. This is a constructivist approach that says that we will build the knowledge that you need to know out of general observations. And finally, and really importantly, this is fun. It's in fact what most scientists get into. The idea that we can look at nature as a series of riddles and attempt to resolve those riddles by careful observation, careful experimentation, and then really detailed reasoning or problem solving is actually where all the fun is in science. So we should not extract that from our class. We should actually put it directly into our classes. So with that understanding, how are we going to do this? The concept development study approach has been developed in detail here at Rice. I've been the lead author on this in a book that we call Chemistry Concept Development Studies in Chemistry. And there's in fact a 2012 recent addition to this. And the good news for you is this book is in fact free. It's available online at Rice's Connexions project, which is cnx.org. If you want to write down the detailed web address for this specific book, it's here on the screen. Or you can just go to cnx.org, and there's a search engine where you can look for concept development studies, and this one will pop up. You can read it online free. You can download it to your reader free if you want. Or if you'd like to have a print copy in a book, you can order it from the website, and the cost is fairly nominal. It's about $20 if you'd like a print version. In addition, you're probably going to want to have any of the sort of standard published general chemistry texts to work through some examples, to see some illustrations, and so forth. What are we going to cover in this class? We're going to cover the material that's typically covered in a first semester general chemistry class, both here and at Rice. I've listed some of the topics here. We're going to be focusing on the atomic or molecular level of matter. We're going to try to understand how we can look at nature as collections of atoms and molecules. We're going to look at the structures of atoms, and then we're going to use our understanding of the structures of atoms to understand the structures of molecules. One of the key factors we'd like to understand is in what way do the atoms combine to form molecules? What is it that holds the atoms together? In other words, we're going to need to understand a theory of chemical bonding. We'd also like to understand the energetics of chemical bonding so that we can understand what it is that makes a molecule stable or what makes another molecule unstable or reactive. And then finally, and very importantly, we're going to understand chemical reactions in terms of the energies of those reactions and what is happening at the molecular level that will cause a reaction to either release energy or perhaps absorb energy. Once you have a copy of the Concept Development Study book, you'll see that we're actually going to cover the first 13 concept development studies, so you can peruse the table of contents there and get a sense for what the coverage of the class is going to be. At the outset, I'll talk about a few foundations of things we're not really going to talk about. First, we're going to understand matter. Chemistry is really actually the study of matter, its structure, its energy, and its changes, its reactions, or its physical changes. Matter, we need to define then, is essentially all the stuff which is around us. Basically, everything is matter. Anything that takes up space, anything that has mass, basically anything in your physical world is matter, and we're going to talk about the structures of matter and the way in which matter changes. We're going to break matter down and focus on a couple of types of matter called pure substances, and two in particular. First, we're going to assume that we've already developed something that chemists developed well over 200 years ago, which is an understanding that there are some types of matter called elements, some types of pure substance called elements. The elements are the fundamental materials from which all matter is made up. There's 115 different elements, but in fact there are only about 40 or 50 that are commonly observed during chemical reactions, and the types that we will talk about here. Those elements are then combined to form compounds, again, pure substances. But by contrast to the elements, where there are only about 115 of them, there are well over 50 million known compounds, and those are all made up by combining the elements in a variety of different ways. Our goal then is going to be to try to understand how do elements combine to form compounds, and even what does it mean that elements combine to form compounds. Although it took an enormous amount of work to figure out which of the pure substances were elements, we're going to assume that all of the elements have been identified. We're not going to walk through that process. Rather, we're going to begin by trying to understand the structure of matter that helps us distinguish between the elements and the compounds, and the ways in which the elements will combine to form the compounds. In the next lecture, the first lecture, we are going to begin Concept Development Study 1, having to do with the development of the atomic molecular theory, and we'll see you there.